part of our chapter deals with reactions that are known as oxidation and reduction reactions. This is probably a brand new topic to most students listening to this lesson. Redox reactions, that's the short word for putting together oxidation and reduction. They're commonly called redox. This is a very common type of chemical change where it's an umbrella of many other recognizable patterns. A redox reaction could also be a type of combination reaction. It could also represent a decomposition reaction. It could fall with a single replacement reaction, and even the combustion pattern. So the last series of reactions with Lesson 2 and Lesson 3 were all double replacement reactions. We started with formation of a precipitate. We did the acid-base neutralization, making a water, and the last little bit there was all about gas formation, the three different driving forces of a double replacement. Now notice the next category called redox. I've listed all the other recognizable change, combinations, decompositions, single replacements, and combustion patterns all fall under this big umbrella known as a redox reaction. What do all of these four different patterns of chemical change have in common? Well, it all has to do with the transfer of an electron through the course of the chemical change. Ionic compounds are formed through the transfer of electrons. An oxidation-reduction reaction involves transferring electrons as reactants move to products. When we think about a transfer of electrons, what we're going to end up looking at is who changed their charge from the left to the right side of arrows. Change of charge. What changed the charge as reactants form products? And that will help us identify what was oxidized and what was reduced. Oxidation and reduction talk about a transfer of electrons. Now, just to remember ourselves, we talked about the Bronsted-Lowry theory of acids and bases, and we talked about that as being proton transfer, and the term conjugate pairs were set up with acid-base chemistry. This is just a side note. Conjugate pairs with acids and bases deal with proton transfer. Opposite of that, when we're transferring of electrons, tracking negative transfer, negative electrons, we're going to look at some redox. So as a step one, before we can write any type of chemical equation that involves transferring electrons, we have to learn what are oxidation states. How do we go about assigning charges so that we can keep track of what's changed? Somebody became more positive as they lost electrons, and somebody must become more negative as they gained electrons. So we're going to begin this lesson by learning how to assign oxidation numbers. It's a simple bookkeeping method. It's not necessarily true of what we find in nature, but it works. So it's a bookkeeping method that we've organized as chemists to come up with a way of assigning these charges, these oxidation numbers, so we can track electron flow. So just a way of keeping track. We need to memorize the rules for assigning oxidation states. So let's begin top of page 11 in our notes, going through these rules one by one. Read them with me carefully, and we're going to make some side notes for each one. Rule 1 reads, the oxidation state of elements in their elemental form, the way we find them in nature, in other words, is always 0. The elemental form of an element is 0. So, for instance, in nature, I would find sodium solid. Sodium solid would have an oxidation state of 0. Hydrogen is one of those lucky 7 diatomics. It is going to be oxidation state of 0. So any element written, an element is a symbol written by itself, not carrying a charge, gets assigned a 0. Keep in mind there are 7 naturally occurring diatomic molecules who would also have an elemental form oxidation state of 0. Number 2, oxidation states for monoatomic ions are the same as their charge. Monoatomic, a single atom carrying a charge. So up here I said, here's sodium atom, oxidation state of 0. What if I had a sodium ion, oxidation state of +1? Ions only exist in aqueous solutions, so I automatically know these are aqueous. Hydrogen ion has an oxidation state of +1. Molecular hydrogen, oxidation state of 0. Hydrogen ion, oxidation state of +1. Chloride ion, oxidation state of -1, and so forth. So the oxidation state for the ions, as we find them on the periodic table and deduce their charge, match their oxidation number. Rule number 3. Oxygen is assigned an oxidation state of -2 in its covalent compounds, except as a peroxide. Then it is assigned a -1. Now this rule is extremely important. Let's take some time with it. Rule 3. Oxygen, we know when it forms an ion, is O-2. I'm going to tell you 99% of the time oxygen's oxidation number is -2. We have this rare exception, and it's worth noting because I see it appear on the AP exam almost yearly. The exception is if we have a peroxide. This is known as oxide ion. What is a peroxide ion? Well, it gives us an example, Na2O2, sodium peroxide. Here we have barium, Ba, was it barium? Let me peek up again. Nope, it was hydrogen peroxide, H2O2. Now I know sodium's a +1, oxide must be a -1, but there's 2 units of it here. So this is just a little bit weird, isn't it? The overall charge here is -2, and that's why we come down and bring that 2. So the peroxide ion is O2, -2. So if I deduce that, give it to the lowest whole number ratio, the overall charge is -1. The peroxide, this is confusing, so I'm really going to try to stress this. This is peroxide. The ion is O2. It overall carries a -2, doesn't it? Because 2 units of a -1 give me an overall charge of -2. -1, 2 of them there, gives me a -2. Since barium's a +2, the compound barium peroxide, BaO2. The compound barium oxide, BaO. So please make yourself a note. This is a rare exception. Peroxides, you're going to notice that it just looks odd to you. Why don't we reduce this down? Well, peroxide itself is O2 carrying a -2 charge. So therefore the single atom of oxygen in a peroxide carries a -1 overall. Rule 3, so important. 99% of the time oxygen is a -2. Once in a great blue moon, we have a peroxide, sodium peroxide, hydrogen peroxide, barium peroxide, and so forth. Rule 4. Hydrogen is always assigned a +1 when bonded to a nonmetal and a -1 when bonded to metals. Another critical rule. Memorize. Let's discuss it to help it kind of sink in. So rule 4, here was rule 3. Let's talk about hydrogen. Oops, rule 4 is what I meant to write. It says if hydrogen is written in the first position, bonded to a non-metal, HCl, I'll do H2S, just based on charge, +1, -1, +1, -2. If I have hydrogen written in the first position, bonded to a nonmetal that carries a negative charge, hydrogen is a +1. This is called the hydrogen ion. Now the flip side of that rule says, What if hydrogen's written in the second position, hooked to a metal? Let's suppose I have NaH. This guy here is now carrying a -1 charge. This ion, we learned, is hydride. NaH, hydride. How about CaH2, calcium hydride? The charge on hydrogen written in the last position when hooked to a metal is -1. Hydrogen in the first position, hooked to a non-metal, carries a +1 charge. Rule 4 is reminding us that hydrogen can be a +1 or hydrogen can be a -1, simply depending on the substance it's hooked to. Rule 5, pretty straightforward, no exceptions at all. Fluorine, always a -1. The most electronegative element on our periodic table, always a -1. Fluoride, -1. Now remember, molecular fluorine, the way we find it in nature, 0. Rule number 1 review. Rule number 5 says if it's hooked in a compound, it's a -1 charge. Rule number 6. The sum of all oxidation numbers in a neutral compound is always 0. We've learned that when we try to crisscross charges, we make an electrically neutral compound. The sum of oxidation numbers in a polyatomic ion equals the charge on that ion. So for instance, let's suppose I have a neutral compound, NaCl, sodium chloride. The number of positives electrically balance the number of negatives to give us 0. Suppose I had a polyatomic ion, I'll just make up chlorate, ClO3, -1. The sum of the two oxidation states, one would come from chlorine, one would come from oxygen, their sum would give me -1 overall. By the way, what would the oxidation number of chlorine be? Rule number 3, oxygen is always assigned a -2. Always, always, unless it's a peroxide, and this is not. So the total negative 3 units here, 3 times -2, the total negative is -6. What must the oxidation number on the chlorine be so that when I sum the two numbers together, I get a -1? What, when added to -6, brings me to -1? Well, it's a +5, isn't it? The oxidation state on chlorine in this polyatomic ion called chlorate is +5. Now, chloride, Cl-, a monoatomic ion, its oxidation number is -1. My goodness, it changes depending on what it's involved with. Chlorine in this polyatomic ion is a +5. Chlorine in this binary ionic compound is a -1. That takes some practice, doesn't it? Let's assign oxidation states to each of the elements in the following, practicing the rules as we go through. Here we have carbon dioxide, CO2. What rule number might play a role here? Well, let's read. Rule number 3 about oxygen. I always start with the oxygen because there's a rule about it. It says oxygen is always assigned a -2. Oxygen is a -2 oxidation number. The total negative then is -4. Rule number 6 says when I sum these oxidation states together for a neutral compound, it ends up to be 0. So what must the oxidation number of carbon end up being so that when I add it to a -4, I land at 0 on the number line? Well, you've got it. Carbon must be a +4. A +4, when added to a -4, is a 0. Starting with the oxygen, we deduce the carbon from it. Let's try another. Here we have nitrate. Oh, maybe I'll just extend the page. It's probably easier. nitrate. NO3, -1. So here's an oxygen. We know that this is not a peroxide, so it's always assigned a -2. Oxidation state of oxygen is -2. 3 units of a -2, 3 times 2 gives me a total of -6. Now remember, this is a polyatomic ion, so the sum of the oxidation states will land at a -1. What must the oxidation number for the nitrogen be so that when I sum with a -6, I go to a -1 on the number line? A +5. The oxidation number of nitrogen in the polyatomic ion nitrate is a -1. How about H2SO4? Well, rule number 3, I like this one. It gives me an idea about oxygen. So oxygen is always assigned a -2. 4 units of a -2 give me a total of -8. This is a neutral compound, so I know that when I'm done, I got to add to 0. Here's hydrogen written in the first position. Rule 4, when hydrogen is bonded to nonmetals, it carries a +1. 2 units of that +1 give me a total of +2. What's the missing number that will be the oxidation state for sulfur? Well, we're going to need a +6. 2 units here plus 6 gets me a total of +8. -8 lands me to 0. The oxidation number of hydrogen, +1. The oxidation state of sulfur, +6. The oxidation state of oxygen is -2. How about this one? Fe2O3. Well, the rule for oxygen, -2. 3 units of a -2 give me a -6. I know it will end to be 0 because it's a neutral compound. I know that the total positive has to be +6. To get me to 0, the total positive is +6. But notice I have 2 units of the positive ion. 6 divided by 2 gives me a +3. Iron's oxidation state is +3. Oxygen's oxidation number is -2. And friends, the last one is an error. Fe3O4 would produce a fraction, because you just please cross that off. It doesn't work. Alrighty. After we cross that off, we have a you try it. What noble gas element has the same number of electrons as the fluoride ion? Well, the noble gas, of course, helium, neon, argon, krypton, xenon. So it's group 8A. Noble gases is the last column in our periodic table. If fluoride ion is F-1, find it on the periodic table, you'll notice that fluorine, element number 9, gains an electron. What noble gas does it become? It's right next door to neon, the end of row 2 on our periodic table. What is the oxidation number of that species? Well, neon oxidation number is an element in its natural state. Rule number 1, we know that it would not carry a charge at all. Fluoride has the same number of electrons as neon. Fluoride gained an electron, carries a -1 charge. Neon, a noble gas, would never gain or lose. Its elemental form gives us an oxidation number of 0. So important to practice assigning oxidation numbers. Let's try some more. First one we have is hydrogen sulfide. Hydrogen sulfide. Chemical formula is H2S. Rule number 2 at the top of our paper, oxidation number for hydrogen. It's rule number 4 dealing with hydrogen. Hydrogen is assigned a +1. So that gives me a total positive +2, making sulfur here a -2. Sulfur in hydrogen sulfide is a -2. Elemental sulfur, S8. This is commonly called flowers of sulfur. Well, here's the big key word right here, elemental sulfur. The way we find sulfur in nature, it's assigned a 0. Any element found in its natural state has an oxidation number of 0. Sulfur dichloride. Sulfur dichloride. Hear those prefixes? This is a molecular compound, isn't it? Knowing that sulfur dichloride is molecular, let's begin with chloride. Knowing where it lives on the periodic table is telling us it's a -1 charge. So the total negative here, 2 units of that -1 give me a -2 overall. So sulfur here must be a +2. First scenario, a -2, then a 0, now a +2. It's changing all over the place. Remember, this is just a way of bookkeeping. It's not anything to do but just bookkeeping. Sodium sulfite. Na2SO3, sodium sulfite. Oxygen rule, -2. 3 times -2 gives me -6 overall, coming from oxygen. Sodium in the first position we know to be a +1. 2 units of that give me a +2 overall. Always leave this middle one to figure it out last. What must be in this position to land at 0? Oh yeah, it's got to be a +4. Oxidation state of sulfur here is +4. And we have one more in our set, the sulfate ion. Sulfate is a polyatomic ion, SO4 -2. The oxygen rule tells us oxygen's a -2, so the total negative is at -8. Polyatomic will sum to give me their overall charge, so that's a -2 overall. What must I add to a -8 to end at a -2? A +6. Sulfur in the last example is a +6. Sulfur gave us an example of an element that changes drastically just depending on the type of compound it's found in. You should pause your lesson here, really take some time to practice assigning oxidation numbers, and when you've mastered that skill, start the lesson again.